All right, so let's continue talking about limits. Today we're going to focus on one-sided limits and continuity. We've sort of already been talking about one-sided limits, so this should not come as a huge shock to you, but we're going to officially put some notation to this now. One-sided limits are denoted as follows. Now, normally we've just seen the limit as x approaches c. Now we have as x approaches c from the left and as x approaches c from the right. I'm going to zoom in here because I know that on the camera, this only shows up so well. Get super close. I know you have your notes, but gosh, even now, even when I zoom, I don't know, I have to redo my focus. Can we see this? Left, right. You have your notes in front of you anyway. Okay, it's fine. I'll leave it. So as x approaches c from the left and as x approaches c from the right, we can even add some notes to this so we know what they mean. So this will be the limit as x. Am I zoomed in too much now? As x approaches c from the left. Oops, left. And the other one's going to be the limit as x approaches c from the right. Not as you're heading to the right, but as you approach from the right. The limit as x approaches c from the right. Zoom back out. Oh no. Whoops. Let me fix this. Oh my. Let's see. This needs to go here. This needs to go about there. All right. Back to reality. All right, so that's your new notation. We're going to be focusing on one-sided limits today. That means that we're really just going to be looking at as we approach from the left or from the right, and then just sort of making conclusions about general limits after that. So let's go ahead and get started here. First, you have one of these awesome graphs, which I know are like so impractical, but they're so good at teaching you about one-sided limits and limits in general. So expect to see something like this on your test. The limit as x approaches 2 from the left of f of x. We're going to look at that first. So as x approaches 2, so I'm looking at this value. And then I'm looking at what happens to the y values as I approach x equals 2 from the left. So I'm going to be moving up here towards y equals 2 as x approaches 2. So as I approach x equals 2 from the left, the values of y are going to be approaching y equals 2. Now, you can see this big gap in the graph. So clearly there's going to be some sort of an issue here. And maybe you're not quite sure about that yet, but we're going to really focus on that today because we're going to be talking about continuity, which I sort of mentioned in the last lesson. For x approaching 2 from the right, we are going to look at what happens to the value of y as we approach 2 from the right. So as I approach 2 from the right, I'm heading on this blue curve up to values approaching x equals 2, and the y values are going to approach 3. Now, you do have this open circle at 3, so that means that the function is not defined as the value 3. It's actually defined here at 2 because that's where the filled in circle is, but it doesn't matter. Remember, the limit is just talking about the values that y is approaching. And in this case, the value y is approaching is 3. So now the last question is asking you just for the limit as x approaches 2 of f of x. Well, you've got a problem here because as you approach from the left, the limit is 2, but as you approach from the right, the limit's 3. So we did an example like this in the last section of notes, and we said that in that case, the limit does not exist because they are not the same on the left and the right. And now we really have some notation that we can put together with this. So we can say now that the limit does not exist because the left and right one-sided limits do not agree. Two is not equal to 3. I think we can all say that. So we're not approaching the same value, so the limit does not exist, and that sometimes happens. Theorem. Let f be defined for values close to c with the possible exception at x equals c. Then we have the following. The limit as x approaches c of f of x equals L, some value L, if and only if, that means it works both ways, the limit as x approaches c from the left equals L, which also equals the limit as x approaches c from the right. So it must be the case that these one-sided limits have the exact same value. And if that's the case, then this limit as x approaches c exists. If the limit as x approaches c exists and is L, then these two must be true. That's basically what this theorem is saying. So for evaluating one-sided limits as a direct consequence of this theorem, many times you'll be able to evaluate one-sided limits like the normal or overall limits. A lot of times you're just going to have this continuous function where we did a lot of these in the last section where we just did direct substitution, no big deal. But we do need to look out for some things like zeros in the denominator. So same thing that we were talking about in the last section also applies here when we're talking about one-sided limits. So we need to look out for zeros in the denominator. Another thing we have to look out for, again, I'm going to bring back your favorite topic, piecewise functions. We need to look at those cutoff or boundary points. For piecewise functions. Because those could have major consequences for us. Like this graph that we just looked at above, this is a piecewise function. It's going to have a different function that's defined depending on which values of x you're looking at. So so this at 2 would have had a major problem, but I mean, think about what happens at 4 though. If you're talking about x equals 4, even though the function value does not exist at 4, the limits agree. The one-sided limits are the same, and we could say that the limit is 2. So it's really just this gap in the graph that's causing any issues for us. And the limit would also exist here at this open circle. The function value is 2, but the value of the limit is 1. We can also say if we end up with 0 over 0, when we have zeros in the denominator, we're going to have to do some algebra and reevaluate. Do algebra. I know I always feel weird saying that, but we just say do algebra. There's just do the algebra. Do the algebra and reevaluate. If we have some sort of a number over 0, remember, if you have a number divided by 0, you end up with some situation where you have a vertical asymptote, which we usually abbreviate to VA. Check to see if the limit is plus or minus infinity. It's going to be one or the other. Okay, so anytime you end up with this situation where you have a vertical asymptote, I mean, remember what that does to a graph. You've got some vertical asymptote sitting somewhere. The values have to approach that asymptote. What values are they? what values is y approaching. So it could do this. I mean, it could, you've seen a ton of these examples. You could have something like this, or you could have them both going the same direction heading down. Any of these possibilities. So you're going to have to check to see what the limit actually is in that case. All right, so let's look at some limits here. I have two big examples for you. They're both going to go on this page. Each one has multiple parts to it though. So if you want to draw like a horizontal line down the middle of your page so that you kind of have an idea of where to cut this off, they're going to be about the same length. Example 1, I'm going to give you a piecewise function because we love them. They're really useful. Negative x squared will be one definition. The other one is going to be 2x minus 5. So we'll look at negative x squared if x is less than 1. And then 2x minus 5 if x is greater than or equal to 1. All right, so we're going to first start talking about limits. And remember that we said that when we're evaluating limits for piecewise functions, we really just need to worry about cutoff values. Or if we ended up having rational functions somewhere inside here, we need to look for values that were excluded from the domain. But in this case, these are both polynomial functions. They're continuous on their entire domains. We really just need to focus on places where we might have issues at this cutoff point. So the boundary point would be 1. Therefore, I'm going to ask you questions about the limit as x approaches 1. It's not going to be interesting for me to ask you questions about the limit as x approaches 0 or 2 or 5 or 1,000,000. It doesn't matter because these are continuous functions everywhere else. We're going to talk a little bit more about continuity in a couple minutes, but right now we just need to figure out what's happening at the boundary where these two functions change. So as x approaches 1 from the left, we're looking at the value of the limit. We're going to look at the function that includes values to the left of 1. If I'm heading to x equals 1 from the left, then I'm heading towards 1 from values that are less than 1, which means this definition. This will go with our from the left terminology. So we'll use that. Let's go ahead and evaluate it. So we have negative x squared. So we'll look at the limit as x approaches 1 from the left of negative x squared. I mean, the parentheses are not essential, but I had this negative here for the left, and then I didn't want them to get messed up. So I'm just going to do direct substitution here the way that I always would. Even though it's a one-sided limit, doesn't matter. I'm still just going to let x be 1. Just be careful not to let it be negative 1. I know that this little negative sign kind of throws people sometimes. So we have negative and then 1 squared, parentheses, exponents, multiplication, division. The exponent gets applied first. So 1 squared is 1. Times negative 1. So this is not negative 1 quantity squared. It's just negative 1 squared. Be careful with that. Your limit is negative 1. Now, the next one we're going to look at, of course, is the limit as x approaches 1 from the right. As I'm approaching from the right, I'm looking at values that are greater than 1. And as I'm going to head down towards 1. So this one will be from the right. That means I'm using 2x minus 5. So I'm looking at the limit as x approaches 1 from the right of 2x minus 5. Now, you might be wondering, like, do we really have to keep this notation on here once we pick the function? I mean, it's not going to change the limit in this case because this function is it's just a line, so it doesn't matter if we approach from the left or the right. But in general, it's just good practice to keep that notation in place. So this will be 2 times 1 minus 5, which is negative 3. The last question, maybe I'm super predictable, but you can see where this is heading. We're going to look at the limit as x approaches 1 of f of x. In order to do that, we're going to think about this theorem that we saw on the previous page that stated that the limit exists if and only if the one-sided limits have the same value. In this case, they don't have the same value. -1 does not equal -3. I know, it's like a breakthrough. They're not the same. They're different values. Because they're not the same, we would have to say that the limit as x approaches 1 does not exist. And then again, that's because the one-sided limits don't agree. It happens. That's okay. If anything, sometimes students like having this conclusion. It's like, oh, DNE, fine, move on. So the limit does not exist. Now, if we had a case where these two had the same value, like maybe both of them were -1, then we would be able to make a conclusion that as x approaches 1, the limit was -1. But that's not the case here. If we were to draw this piecewise function, we were to look at the graph, you would see that as x approaches 1 from the left, the y value would approach -1. And as x approached from the right, the y value would approach -3. So this would be one of those graphs that has a gap in it where it's not a continuous graph. I keep talking about this word continuous, which we haven't officially defined yet. But I think saying that something is continuous, I think is pretty intuitive for students. You know when things are continuous. It means they don't stop. Example 2. G of x, let's look at a rational function here, is x cubed minus x squared minus 6x divided by x squared minus 9. We're going to look at actually 4 different limits here. Because why not? Oh, yikes. Sorry. Move you down there. Excellent. Wonderful. The first one we're going to look at, it will be x approaching -3 from the right. Now, if I'm approaching -3 from the right, in this case, the numerator and the denominator here are both polynomial functions. I'm just going to go ahead and plug this value into this function for direct substitution. I'm going to rewrite my rational function over here. And let's go ahead and evaluate it, and we'll see what happens. When I say let's see what happens, that's usually like an omen, like maybe something not so great is going to happen, but it's going to be really instructive, I promise. So we're going to take -3 cubed minus -3 squared minus 6 times -3. Lots of signs to keep up with here, so be careful. Now, you might be noticing already that there's an issue here with the denominator. There's a reason that we're not talking about this limit as x approaches 1 or 2 or 0. We're talking about it as x approaches -3. The reason we're doing that is because there's a problem at -3. This is a value that makes the denominator 0. -3 times itself is 9, and 9 minus 9 is 0. Now, your next order of business is to look at the numerator. If the numerator is equal to 0 also, then you have an indeterminate form. An indeterminate form is not 0. But we're going to see what we get when we evaluate the numerator. And if we get a number, well, we know a number divided by 0 means we have a vertical asymptote. 0 divided by 0 means we need to do a little bit of algebra on this function. So I'm going to go ahead and evaluate this using a whole bunch of parentheses. Let's see, I've got -3 cubed minus -3 squared. If you're entering negatives in your calculator, make sure you're using an actual negative sign and not a minus sign. I've had so many students get syntax errors and they're like, I don't get it, it's not working. That's because they're using a minus sign. See the difference? This one's a minus, that one's a negative. Down here. Okay. Most of you will know that, but if you don't know that, I'm glad I just told you. So this is a number divided by 0, which means that if we take a number and we divide it by 0, we're going to have either plus or minus infinity. So we need to figure out what the situation is with this limit. This means that we have a vertical asymptote at x equals -3. Remember that this is something that was discussed on the previous page. We said that we're looking for values where we might have zeros in the denominator. If we have 0 over 0, we're going to do some algebra and reevaluate. Well, we don't have that case, but we got a number over 0, which means that we have a vertical asymptote, and we're going to check to see if the limit is plus infinity or minus infinity. So that's what the goal is now. And if you're kind of like, well, how would I know? You're going to have to graph it on your graphing calculator, or you could use a table of values and approach -3 from the right and figure out what's happening there. You decide. I'm just going to look at the graph because that's the fastest and easiest way to do this. I'm going to go to my y equals, and I'm going to plug in this function. I'm going to be very careful to make sure that I put parentheses around the numerator and the denominator. X squared minus 9. So x cubed minus x squared minus 6x divided by x squared minus 9. The whole numerator is in parentheses. The whole denominator is in parentheses. And we will graph it. Okay. So we've got this vertical asymptote, which we already knew existed at x equals -3. You can see that here. So now we're going to figure out, well, what's actually happening to the function? Well, as we approach -3 from the right, the y values are going to go up, 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 up to positive infinity. They're going to go up forever following this vertical asymptote. Now, this is only because we're approaching -3 from the right. And that puts us on this leg. Up from the right means I'm heading up. So we would say now that this limit from the graph, the limit is infinity. So don't say does not exist. Give me a conclusion. Yeah, it's true. The limit does not exist, but tell me where it's heading. You know, we can't actually narrow in on a value, but tell me where it's going. I mean, if you're going to say does not exist, that applies to something like this, where the one-sided limits don't agree. You can't conclude anything else. But here we can give some sort of direction for where y is heading. Now for b, we're going to look at the limit as x approaches -3 from the left of our function g of x. Now, we already plugged in -3 for direct substitution, and we got -18 over 0. So we don't need to do that again. I mean, you'll know what it is. This is from part A. So what we're going to do is we're going to look at the graph, and we're just going to see what's happening to the value of the limit. So we just looked at this just a minute ago. As x is approaching -3 from the left, your graph is heading down. Now, you can always zoom out if you want to see that a little bit more clearly. And let's say sometimes I like to zoom kind of depending on where the center of this picture is. So I'll scroll over and I'll be like, I kind of want this to be the center because it's like smack in between those two curves. So, oh, got a little bit ahead of myself. I didn't hit the zoom button. If you hit zoom and then you go zoom out, well, now I'm scrolled over to the center. I can hit enter and it'll zoom out for me. So you can get a little bit more of a picture of what's going on. If that's too much, you can always just adjust your window settings to whatever you want it to look like. But now we can see that as x approaches -3 from the left, the y values are heading down. So we can only get as far as values that look like they're close, and then they're going to head all the way down to -infinity. So the limit is -infinity. And this is something that we obtained from the graph. Now, of course, I'm going to ask you this question. The limit as x approaches -3. This is not a one-sided limit. This is just the limit. And you are going to say, well, let's look at the one-sided limits. The right-sided limit went to infinity. The left-sided limit had values that went to -infinity. They're not going to the same place. Therefore, we would say that that limit does not exist because the left and right limits do not agree. Now, if you ended up having both sides go to positive infinity, or maybe both sides went to negative infinity, then you could make a conclusion. But in this case, you can't conclude anything because these are not the same. Let's add one more part to this because I want to go over that other situation. Let's look at the limit as x approaches +3. And we'll look at it from the left. So I know sometimes all these little negative signs can look so confusing. We were here approaching -3 from the left, -3 from the right, -3. Now we're approaching +3 from the left. And we will put this function back in now since we're going to really look at this again. So notice that we have those two values where we had a situation where the denominator was going to be equal to 0. And one of those values is at 3. So if we go through and we use direct substitution, because 3 is positive, I'm not going to put parentheses on everything. The denominator value is going to be 0. And in the numerator, you have 3 cubed, which is 27, minus 3 squared, which is 9, and then minus 18. So 27 minus 9 minus 18 is 0. Now, remember what you're supposed to not do. When you get 0 over 0, you're not supposed to say equals 0, check, and you put a box around it. Don't do that. 0 over 0 is not 0. And I also don't want you to say, oh, 0 over 0, DNE, next. Don't do that. If you get 0 over 0, do algebra and reevaluate. Let me tell you though, do algebra basically means somehow you need to get rid of this indeterminate form. So when we do algebra here, we're going to take out a common factor and rewrite this function as something a little bit simpler. We did this also in 2.4. So I'm going to take x cubed minus x squared minus 6x. I'm taking it out of the limit for a second. Over x squared minus 9. And I'm going to rewrite it by factoring. I can take out an x in the numerator. In the denominator, I can rewrite this as a difference of 2 squares. Sorry, my dog is like, maybe you wouldn't even have heard that. I don't know. But it's like really loud to me. Scratching over there or something. All right, so now I need to factor this as -3 and +2. Check this because this is one of those things that students like to factor wrong for some reason. I don't know what it is about this combination of numbers. I think it's because if the 6 is positive, you get different, you can use different values, like, or maybe if the 1's positive, I don't know. I can't remember. I'll think about it later and it'll come right to me. X squared plus 2x minus 3x is -1x, and then -3 times +2 is -6. X plus 3, x minus 3. Cancel out your x minus 3's. In general, when you get an indeterminate form, you just try to eliminate it by rewriting the function. Now we'll take the limit again, this time using our new function, x times x plus 2 divided by x plus 3. You can leave it factored. It's fine. So this will be 3 times 3 plus 2 divided by 3 plus 3. 5 times 3 is 15. 3 plus 3 is 6. So you get 15/6. And if you're kind of wondering, oh, we can reduce this, by the way, to 5/2. If you're like, huh, that's weird. How do we go from indeterminate to a number, and how is it possible that we were dividing by 0 and we still got a number? Well, look at this graph. I'm going to take this back to our standard zoom, by the way. Zoom 6. All right. So when we're looking at x equals, this is something that you should have done in algebra, but I'm reminding you of it now. When we are looking at x equals 3, you get this value of 5/2, so it's 2.5. Looks good, right? It looks like the function value. When you go to your table and you enter the value 3, you get an error. Well, watch this. That was my original function, right? Let me put in the new function. X times x plus 2 divided by x plus 3. Don't forget to put parentheses around your denominator. Now, this is going to graph in red. I'm not sure how well these colors will come out, but watch what happens. If the colors don't come out, you're like, what happened? Nothing happened. No, something did happen. The graph graphed over itself because these two are actually the same function. One of them just has a discontinuity at 3 and the other one doesn't. If I go to my table now, y sub 2 was our new function. Remember, I put that in y sub 2. And when I look at that in the table, I entered 3 and I get the value of 2.5 on the new function. When we redefined the function, we eliminated that hole that was in the graph on the original function. So a lot of times, if you end up with an indeterminate form with a rational function, it just means that you have a hole in your graph at that point. You kind of cancel out the value that gave you the hole, and then you can reevaluate it and get the limit. Because remember, even though the function value didn't exist, the limit still existed. I mean, if I were to go through and take this graph back out, you wouldn't have known the difference. It looks exactly the same. And you can't see that there's a hole at x equals 3, but there's a hole there. So we redefined the function. We didn't have to worry about it. It's almost like this little gap. Boop. Your calculator just can't discuss it because the pixels are so little. Or maybe they're not little enough, but either way, you won't be able to see that little tiny blip in space at that very one exact point. All right. So that was a really good example. Now I keep talking about continuity. Let's talk about the actual definition of continuity. First, I'm going to give you the layman's way of discussing continuity. All right. So the intuitive or graphical idea is a function is continuous at x equals c if you can draw its graph at c without lifting your pencil. That's the idea. If you can draw its graph at c without lifting your pencil. So we looked at this graph earlier, and I talked about how awesome it was. But notice that if I was trying to graph this, I'd have to lift my pen here and go over this hump. I could keep drawing and drawing and drawing, and now I've got not only just a hump to go over, but a gap. And then I would draw, I've got another hump, and then I could keep going. See, we actually have 1, 2, 3 places where this function would be discontinuous. We're going to talk about those in a couple minutes. Before we get to that, we need to actually talk about the real definition for continuity, the mathematical definition, which I know is very boring for you, but it should be really interesting and exciting. A function is continuous at C if f of C is defined. If C is defined. If the limit as x approaches C of f of x exists. And if that limit equals f of C. So there are 1, 2, 3 conditions for this. So we'll write those down. So the first thing is that f of C is defined. The next one is that the limit as x approaches C of f of x exists. And then the third one is that f of C, the function value, is equal to the limit as x approaches C of f of x. So officially, in order for any function to be continuous at a point C, all 3 of these need to be met. If you can just find one of these conditions that isn't met, you can say, all right, this function's not continuous. Moving on. If you can show that all 3 of these are true, then you can go ahead and state that your function is continuous at those points, whatever points that you're examining. So let's do this for a real graph, for a graph. So I already stated that we've got 3 problems here. One of them is occurring at 4, the other one's occurring at 2, and then there's another one at 1. These are the 3 places where if we were trying to draw the graph, we'd have to lift our pencil. And yes, we have to lift our pencil at an open circle. There's nothing there. Remember, it's a hole in the graph. And here's a big gap. And then here it'd be like, boop. I once had a student who referred to these open circles in the graph as like potholes in the road. So if you were driving along a road, you're working your way through and all of a sudden, boop, you hit the pothole and your car has to kind of go over it. I know your car doesn't really jump over it, but you're airborne for like a split second. It's kind of like that. So I don't know. That always kind of stuck with me. Let's go from left to right and talk about this first point first. X equals 1. So we're going to look at these 3 conditions and determine how this relates to our point x equals 1. Now, we already know it's not continuous because we can't graph it without lifting our pen, but we're going to show this mathematically. So for x equals 1, we're looking at the 3 conditions. And so I'm going to ask, is f of 1 defined? Officially, there is a value of f for x equals 1. So yes, technically f of 1 equals 2. Yes, f of 1 equals 2. Check. All right, so it's defined, so we don't have a problem there, but we know there's going to be a problem somewhere. So if you're like, oh, this is a bummer, sorry, we got 2 more conditions to check. The second one would be, does the limit as x approaches 1 of f of x exist? So you're looking at this graph and you're like, all right, well, as I approach 1 from the left, yeah, the limit is 1. And as I approach 1 from the right, yeah, the limit is 1. The y values approach 1. Yes, the limit as x approaches 1 of f of x equals 1. Check. Okay, so what's the catch? Well, it's condition 3. It must be the case here that the value of the function is equal to the value of the limit. So you're going to ask yourself, does f of 1 equal the limit as x approaches 1 of f of x? Well, we just said that f of 1 was 2, and the limit as x approaches 1 is 1. So that's not true. We would say that 1 does not equal 2. Thus, condition 3 is violated. So we would say that f is not continuous at x equals 1 because the limit as x approaches 1 of f of x is not equal to f of 1. So if you're asked to prove that a function is not continuous at a point, you're going to find one of these conditions that's violated. In this case, it's condition 3. Sometimes you'll find more than one condition. For instance, we've got a big problem at x equals 2. So I'm going to look and see, first of all, is f of 2, condition 1, is f of 2 defined? So you're going to look and you're going to say, I don't know, let's see. F of 2 is defined. Yep, we've got a function value there. F of 2 is 2. Okay, fine. Yes. F of 2 is 2. Okay. The next thing we're going to determine is, does the limit as x approaches 2 of f of x exist? Well, you're going to look at this and say, okay, as I approach 2 from the left, the limit is 2. As I approach 2 from the right, the limit is 3. The limit does not exist. The limit as x approaches 2 from the left of f of x equals, what did I say, 2, which does not equal the limit as x approaches 2 from the right of f of x, which equals 3. So the one-sided limits do not agree. Therefore, the limit does not exist. Thus, f is not continuous. You can abbreviate that at x equals 2 because the limit as x approaches 2 of f of x does not exist. Okay. Now, once you've found one condition that's violated, you don't even need to look any further. You don't have to check condition 3. We've already stated that this condition is violated. We're done. All you need to do is violate one condition. You don't need to do any more work at that point. The last issue we have occurs at x equals 4. So we're going to check these conditions for 4. The first thing we're going to check is whether or not f of 4 is defined. Do we have a function value at 4? And you're going to look, you'll be like, wait a second, I don't see anything. There's a big open circle at 4, and there's nothing else going on. The function is actually not defined at 4. So you would just say, no. F of 4 is not defined. There's a hole. There's no other point where it could possibly exist. So you would say, thus, f is not continuous at x equals 4 because f of 4 is not defined. Do I have space? I was going to add something to this graph. I didn't think about it till just now. Yeah, we have a little space. Okay, here, do this. Let's see. We'll do 5 and maybe we'll call this 6. So I moved that a little bit over. That's okay. We'll do the best we can. Let's say that I have this graph going down and it approaches a vertical asymptote at 6. And then maybe from the other direction, the curve will come up. It's got a horizontal asymptote at 0 and a vertical asymptote at 6. Can we do that? We'll add to this. And then we'll talk about, I mean, clearly the graph is not continuous at x equals 6. Clearly, like, couldn't be any bit more straightforward there, but we need to talk about it mathematically. So we'll say that as at x equals 6, we're going to check, is f of 6 defined? No. Again, this took one condition. It's not defined. You don't need to worry about it. It's not defined. The limit does not exist. Therefore, the limit can't be equal to the function value. There's no, I mean, there's nothing about this that says that it's continuous. So f is not continuous at x equals 6 because it's not defined. So you might see something like that with a vertical asymptote, just so you know. All right, the last page here, I'm going to talk about continuity. Okay, when looking for points of discontinuity algebraically, there will always be a discontinuity at places where the denominator equals 0. I know I keep writing that over and over again, but it's important. Keeps popping up. At places where the denominator equals 0, and there will sometimes be a discontinuity, sometimes, not always, at cutoff points of piecewise functions. Cutoff or boundary points of piecewise functions. All right, so those are the places where we're going to be looking at these issues for continuity. I'm going to give you 2 examples on this page, and then we will be out of here. Example 1 is f of x equals x squared minus 25. I don't know why I love this example so much. I couldn't tell you why. I just really like this example. X squared minus 25 over x squared minus 5x. All right, we're looking for points of discontinuity in this graph. You know what I think I like about it is that we can say so much about a graph without even having to look at the graph itself. We can just look at the function and just be able to say so much. And we're going to be doing so much more of that as we head into even chapter 4 and just really learning how to identify those characteristics. Sorry, I'm going off on a tangent here, but I get very excited about math. All right, I'm looking at places where the denominator might be equal to 0, and that's going to lead me to places where I'm going to have some discontinuities for sure, whether it's a vertical asymptote or maybe just a hole in the graph. Either way, we need to look out for some of these places. So let's go ahead and take our denominator and set it equal to 0. Now, remember, this is a quadratic function. Sometimes students, oh, you know what they do? I'm going to do this. I'm going to say, don't do this. Do not do this. Look at this. I'm narrowing my eyes at you because I really want to make sure you don't do this. Okay. They add 5x to both sides, and then they divide by x on both sides, and they get x equals 5. Don't do this. You don't want to divide out a variable. You're dividing out possible solutions when you divide out a variable. What you want to do is anytime you are trying to solve a quadratic equation, you can always solve it by factoring. But remember, with quadratic equations, you always want to have 0 on the other side of the equation. For linear equations, you want to bring variables over like that. But for quadratics, just solve it by factoring. Using the 0 factor property, you get x equals 0 and x equals 5. So you still do get the x equals 5, but if you do it this way, you cancel out a variable, you lose the solution x equals 0. So just watch out for that. I see students do it all the time, just not realizing that they shouldn't do it. Okay, so these are the 2 values where we're expecting to have a discontinuity. Now, we need to determine what is actually happening at these 2 points. To do that, here's my suggestion. We're going to take our function and we're going to rewrite it. I can rewrite the numerator as x plus 5 times x minus 5 using the difference of 2 squares. And then we already said we can rewrite the denominator as x times x minus 5. When you cancel out your common factors of x minus 5, that leaves you with x plus 5 over x. This means that because we were able to cancel out the discontinuity at 5, that means that we would actually have a hole in the graph at x equals 5. We still have a discontinuity at x equals 0. If you can't cancel it out, it's a vertical asymptote. If you can cancel it out, it's a hole. We canceled out. We canceled the factor x minus 5. So x equals 5 is a hole. Now, a hole is still a discontinuity, but it's not a vertical asymptote. So I guess I technically didn't tell you to specify. I just said find points where the function's not continuous. And we just did that. X equals 0 and x equals 5 are values that make the denominator 0. These are your points of discontinuity. So we're going to say that these are values where f is not continuous. So I want to be clear about this. They're both discontinuities. One of them, we just happen to be able to cancel out. That doesn't mean that it's no longer a discontinuity. It just means that if we canceled that factor, then the value that we got from that factor is a hole. If we can't cancel it out, we've got this discontinuity we can't get rid of. It's a vertical asymptote. So whether or not I'll have you specify that on a test, I don't know. We'll see. I'm going to see. If you don't have homework questions that are asking you that specific thing, then I wouldn't ask you about it on a test unless it was extra credit. Sorry, that was like an elongated wink. All right, I got one more for you. It's a piecewise graph because we have to do another piecewise example. Otherwise, our day will not be complete. All right, so we have example 2. G of x equals, this one's going to have 3 definitions. 0, 3, and the square root of x plus 3. So we have x equals 0 or y equals 0 if x is less than -3. G of x equals 3 if x equals -3. And g of x is the square root of x plus 3 if x is greater than -3. That's your definition. All right, now we can talk about points of discontinuity. You're only really looking at one value. Y equals 0 is a horizontal line. Y equals 3, well, if it exists only when x equals -3, it's a point. The square root function is continuous on its entire domain. Now, the domain of this function we talked about in the first section. Remember that we just need whatever's under the radical to be greater than or equal to 0. And that means x has to be greater than or equal to -3. So all of these values here are in the domain of this function, and the radical function is continuous on its domain. So, you know, the square root function just kind of, we talked about its graph. It's going to be shifted to the left 3 units, and it's going to look like this. So we don't have any issues with the continuity there. Mostly, we're just focusing on this piecewise function. You know what? I already just graphed this. I said that occurs if x is greater than -3. So this would be an open circle. I mean, you could just plot this piecewise function right now. If x equals -3, y is 3. So you'd have a point like somewhere up here. And then if x is less than -3, you would just have 0. So any value of x that's less than -3 would just be y equals 0. So that's what the piecewise function looks like. So now that I've plotted it, you're like, wait a second, I can see the problem. It's not continuous because there's an open circle at -3 and the function is defined somewhere else. Yeah, that's true. Graphing it is absolutely one way of getting to that conclusion. But another thing you could do is look at those 3 conditions for continuity. And officially we should do that because we just learned those. We should use them. So we know the issue occurs at the boundary. We know if there is a discontinuity, it's going to occur at the boundary or the cutoff point. So we're going to examine x equals -3. And we're not going to have anywhere else on this graph where we could possibly have any other discontinuities. So it's got to be this one if it's any one. So in order to do that, we're going to look at these 3 conditions. I'm going to determine one is f of -3 defined. Yes, we know that as long as x is equal to -3, g of x is 3. So I'd say yes. Oh, not f, sorry, I keep saying f, but it's actually g. G of -3 equals 3. So that's not a problem. The next one is, does the limit as x approaches -3 of g of x exist? Well, you're going to go through and determine that. So we're going to do that by looking at the one-sided limits. So we're going to check the limit as we approach -3 from the left. As I approach -3 from the left, you could always look at this graph, or you could look at the definitions. If I'm approaching from the left, I'm approaching from values that are less than -3. That means I'm looking at the function 0. And the limit of a constant is just constant. There's nowhere to plug that variable in. Now we'll look at the right-sided limit. The limit as x approaches -3 from the right is actually going to be following this function. This one follows values that are greater than -3. So I'll plug in the square root of x plus 3. And then when we evaluate this, the square root of -3 plus 3 is the square root of 0, which is 0. Well, the one-sided limits agree. So I would have to say, yes, the limit exists. The problem is going to occur on that third definition for continuity. The third definition states, is the function value, I just called it f again, and it's g. You know, I'm going to have to go through and rename everything f because I call everything f. Is g of -3 equal to the limit x approaches -3 of g of x? And then you're going to check, and you're going to say, well, g of -3 is 3. Is that equal to this limit value? Nope. Because the function value is not the same as the value of the limit, we would say, hence, g is not continuous at x equals -3. Okay. Oh, you know, if you wanted to go back and use that same logic on example 1, you could just say that the function values don't exist. So really, there's not a whole lot that we have to do as far as taking the limits there. We would just say that f of, sorry, I should have done this earlier, f of 0 and f of 5 are not defined. So officially, that's what we would have done using that definition for continuity. Okay, but down here, and you can see this from the graph as well, the limit exists. You do have that, you know, as we approach -3 from the left and from the right, the y value is 0, so the limit's 0, but the function is defined as a different value. Now, if I would have instead said that g of x equals 0 as x equals -3, Or if this conclusion would have just been gone altogether, we could have said that g of x is 0 if x is less than or equal to -3, then we would have had continuity. But the pure fact that we move up to 3 at this point means that the function's not continuous. We got a hole in the graph. We can't draw it without lifting our pen or pencil. All right, that's one-sided limits and continuity, right? Next time, ooh, look at this. Next time we get to talk about the derivative. So we're getting into the fancy schmancy stuff very soon. All right, I will see you next time. Let me know if you have questions on that homework. Have a wonderful rest of your day.